Hello, it's Keith here, and today we're going to be looking at how to do a Hello World program in a single assembly file on the Sega Master System and the Sega GameGear. Now, in case you're not familiar with the technicalities of these systems, they're virtually the same machine, so with very little changes we can make a program that works on both. That's exactly what we're going to do today. So let's actually see the program running. So here's the Hello World example running on the Sega Master System emulator here. You can see Hello World. And then if I just change to my... And you can see here we've got Hello World running on the GameGear. So we can basically write this one program that does both. Now, we've been doing Hello World on a variety of systems, and this one's going to be a little bit more complex than the others. The reason for this is that the Master System and the GameGear basically don't have any firmware, so we have to do everything ourselves. So what we're going to do today, though, and it's not going to be too bad. So the first thing we're going to do, well, this program we're building is going to create a ROM file, and that will actually effectively be the entire firmware of the system. So we're actually starting at memory address 0. When the GameGear or the Master System switch on, they will start running the code at memory address 0. And what we're going to do is we're going to jump over this area here to our program start here. And this area here is entirely C9s. C9 is a return. Now what we're doing here is we're setting the RSTs and the interrupt handlers, the non-manageable interrupt and RST7, to just returns, just in case they get executed. Now if you're not sure what that means, don't worry about it, but it's just something that's a good thing to do to start off our program code to reduce the problems while we're just getting set up and working out what we're going to do. So we're going to start at this point here. Now this is effectively hexadecimal 0080, but we don't really need to know that because we're using a label and we're just jumping to this label. We're then going to turn off interrupts because we don't really want interrupts running. We're going to set interrupt mode 1 just for safety, and then we're going to load a valid stack pointer. We're going to load the stack pointer as DFF0, which is near the top of the memory of the SMS or the GameGear. So that's where we're going to use for our stack pointer, because if we didn't do that, we wouldn't have a valid stack. Okay, now what we need to do is we need to turn on our screen. So we need to send various control values to the VDP hardware. Now the VDP hardware uses two ports, a control port and a data port. Now it's actually only the control port we need to send these initialization values, and we're going to use the OTIR command. This is out, increment and repeat. What it does is it loads in values from HL, and we're pointing to a label called VDP init data. We'll see that in a moment. It uses B as a counter, so we're counting the length of the data here just with a subtraction. And then it writes to C, and we're pointing C to the control register. And then OTIR will just run repeatedly until B reaches 0. So here's the data. Now we're not going to go into this, but we need to set some valid startup data to get the screen to turn on basically. So we're specifying default addresses for the tables, the pattern map and the tile map that actually make up our characters of our font, and where the screen's going to be set to which tiles are showing which letters, things like that, and or turning the screen on as well. So we need this kind of stock data as a minimum to get the screen working. Now at this point we've actually turned the screen on, but we won't still be able to do anything with that because we won't have any colors even, so all the colors will be black. So we need to set some colors. Now what we're going to do now is we're going to set them to color RAM. Color RAM is from C000 onwards. These are sort of registers that define the colors. We're going to use a command called prepare VRAM. This is a function I've written that selects the memory address that we actually want to write to in VRAM. So here's the command, and essentially what we do is we execute this with a HL value, and this will then execute and select that as the next destination for our writes to VRAM. Now we're not really going to go into it today, but the video RAM is basically set up like this. It's a 16-bit address range in theory, but actually there's only 16K of memory here and the color data. But the important thing to understand is, of course, this isn't related to the Z80 memory. This is separate memory altogether. And we select the address to write to by outputting to VDP control, these values here. And we have to add hexadecimal 40 to the high byte to say that we want to write, otherwise we'll be reading. And then once we've done this, we then out the bytes that we want to write to that memory address using out commands to VDP data like this. And so, as I say, we're accessing the VRAM via the out command, not via normal memory writing in the case of these machines. So what are we going to do? Well, we're going to use palette data, which we're pointing to with HL, and we're using OTIR again. Now, rather than before where we wrote to VDP control, with the prepare VRAM, we use VDP control to select the port, but we actually write the data to the VDP data this time. The interesting thing is you'll notice that if we're writing to the master system, we're going to write 16 bytes, but on the GameGear, I'm defining this build SGG symbol. I actually define this on the command line. We'll have a look at this in a moment. But when I'm compiling for the GameGear, I define this symbol on the command line. And so on the GameGear, we'll be compiling this code and we'll be writing 32 bytes. On the Master System, we'll be writing only 16. Why are we writing more bytes on the GameGear? Well, the GameGear essentially only has two differences to the Master System. It has twice the number of bytes used for the colors. The color definitions are more advanced, and also the screen's smaller. Now, the extra areas of the screen do exist, but you can't see them. So we're going to see some changes later on. But as I say, at this stage, we're having to send more palette data. Now let's take a look at that palette data. So here's the two versions of the palette data. So this is the Sega Master System version. We got 2 bits for red, 2 bits for green, and 2 bits for blue here. And then the other 2 bits are unused. On the GameGear, we've got an entire nibble, 4 bits for red, 4 bits for green, 4 bits for blue, and 4 bits unused. And as I say, 2 bytes per definition, just a single byte. So we're defining 16 definitions here. 0 is the background, and our font is using number 15 here, and we're defining our font as yellow. So this OTIR command is writing that entire palette definition of either 16 bytes or 32 for the GameGear. And once we've done this, we've got our colors set up. So now we're actually getting somewhere to actually drawing some fonts, maybe. Okay, so what's the next stage? Well, we've got colors, we've got background, but we've got nothing to show to the screen. We need to define some patterns. And so what we're doing is we're using a bitmap font. So we've got this label bitmap font. And we're loading in this font here. We're including it as a binary. Now, this is a font file that I've used in my tutorials quite a lot. It's essentially a 1 bit per pixel font, a black and white font. Now, the Master System GameGear are 16 color machines, so they're 4 bits per pixel. They use bit planes, and this basically means that we have to make 4 writes consecutively. Each one defines a single bit of 8 pixels, and the 4 added together will make up 4 bits, 16 colors. Now, if we've just got a single bit plane, a black and white image, we can write those bytes 4 times, and that will effectively set all of the colors to 0 or 15. I know that's maybe a little bit tricky if you're just starting out, but you should be able to use this code as is. So this is where we're writing our font. So we're not using OTIR because OTIR would only send data as is. We're modifying our data slightly because we're writing that single byte of data 4 times to make 4-bit planes. So we're writing the data increasing HL, decreasing BC, and then repeating until it reaches 0. So this is just writing that bitmap font into the pattern data. We're now actually getting somewhere. We've got pattern data of a font in memory. Okay, what do we do next? Well, we're defining 2 variables, next character X and next character Y. We've got no code to actually draw our characters to the screen, so we're going to have to calculate the location ourselves, work out where in memory that is, and then draw the letters as we want them to that position. So we're defining 2 bytes of the memory of the system in RAM, C000 and C001 as X and Y. Now, on the master system, we just want to write to the top corner, so we set those both to 0. But as I said, the GameGear screen is smaller and it's centralized, so we need to set 3 as the Y position and 6 as the X position, which is the visible top left of the screen. Okay. So we've now got a font, we've got a cursor position, we've got colors, we've got a screen that's switched on. How do we actually print characters to the screen? Well, essentially what we need to do is we need to work out the memory location that we need to write to set a tile to show one of our patterns, our pattern being our font. So the tile map is at 3800 just here, and I'll tell you each definition in there is 2 bytes. So one tile is 2 bytes. So the top left tile on the master system is going to be at 3800. One tile to the right of that will be 3802 and so on. So effectively we want to multiply X by 2 and add Y times 64 because there's 32 tiles wide on the screen. That's true of the GameGear of course as well, just that some of the tiles aren't visible. So what we're going to do here is we are going to take X and Y, load them into B and C, and we're going to bit shift them around and add them together. And effectively you can see we're loading in Y here, shifting it to the right twice, and then we're shifting X to the left once, merging those together, and this together will effectively calculate the XY offset within the tile map that we want to write to. So we then add the base of the tile map, hexadecimal 3800, and we run that prepare VRAM command again, because just like when we were writing bitmap data or color data to the VRAM, when we want to set a tile, we're writing to the VRAM. So we're now going to actually store our character to the screen. Now our character is in AF, but we backed it up here. Now our font, the font file that I'm using in these examples, has no characters below 32, so we're subtracting 32 to compensate for that. And then we're outing the pattern number to the VDP data port. So if it was a space, it would now be a 0. If it was exclamation mark, I think it'd be 1. So we're then writing that as the first byte. As I said, each tile definition is 2 bytes. The second byte has extra palette options, and there is the capability for 9 bits of tile definitions, 0 to 511. But we're not using that in this case, so we just write a 0 byte as the second byte for our tile definition. That's now shown the character to the screen. So we increase the X position. Check if we've reached the end of the screen, which is 32, the full width of the tile map on the Master System. It's 26 on the GameGear because, as I've said, it's a centralized screen, but the screen is much smaller, so we need to check a bit earlier. If we've got to the end of the screen, we're running a new line command. The new line command is very straightforward. We're just setting the X back to the far left, 0 or 6 on the GameGear, and we're moving the Y position down 1. Now, I know all of that is a bit complicated, I apologise, but as I say, that's what we've got to do. But now we've got a command that can create a character on the screen. Well, once we can create a character, we can create a string. So that's what we're doing. We're loading in characters from HL. Our string is 255 terminated, so when we get to a 255, we return. If we haven't got to a 255, we keep printing the characters until we do. And that's how our print string routine works. So to show a string to the screen, we just load HL with message and run print string. And if we just add this a second time here and we just run it, you can see we're now showing hello world twice. And if we did a call to the new line command, we can now show it on 2 separate lines. So you can see here that once we can print characters and strings, we can have maybe a little bit of fun and get things started a bit. Now we looked at the header, which was essentially the initialization of the program code, but we do need basically a footer to the ROM. And now this defines some attributes of the ROM. Now, in all honesty, they're hardly used on the systems at all. There's a lot of settings here, but most of the Sega Master Systems ignore them, or some of the Game Gears ignore them. So it's only really certain Game Gears and the export master system that check these at all. If you're not using those, or if you're using an emulator without a ROM, you don't need this. You can just completely ram out this section. But for completeness, we're going to have a look at it. So the ROMs on the Master System and the Game Gear can be different sizes. They can be 16 kilobytes, 32 kilobytes, all the way up to 512 kilobytes. I'm defaulting to 32 kilobytes for simplicity. But if the ROM is bigger, if it's a 512 kilobyte ROM, then this kind of footer thing actually still appears at the same memory address, 7FF0 here. So basically in the middle of the ROM almost. So it's a fixed position irrespective of the size, although if the ROM is less than 32K, it does relocate. Now the first thing that appears is the text TMR Sega. Some Sega Game Gears check this, the ones with a firmware ROM, but most don't. But you really want to put it there. Then we've got a couple of zeros. We've got 2 bytes here that I've set to hexadecimal 69 twice. They're supposed to be a checksum. Now, some of the Master Systems, the international ones, do check this, and I'm going to show you how to put a valid checksum in there later. Now, beyond that, we've got some product version codes here. We can just set those to 0. And then we've got some bytes that define what kind of system it is. So I've got it set to either Game Gear export, 32 kilobytes, or SMS export, 32 kilobytes. And the way it works is the top nibble here is one of these numbers, 3 to 7. And the bottom nibble is one of these here, CF0 or 1. And there are a few very rare alternatives as well. But essentially, we're setting it to 32 kilobytes and one of these systems here. Now, this works fine without anything. But what happens if I change this to an international system and I've actually got my firmware set up so that the emulator will use a firmware? And you can see this firmware action showing that Sega logo. You get a noise noisy effect there. And now we get a software error. Well, what has gone wrong? Well, I haven't given it a valid checksum here. I haven't changed that, so we've got an error. And this is where we're going to look at my compiling scripts here. We've got SMS and GameGear here. Now, they're both basically the same. The only difference is the name of the file. If it's got a .gg, then the emulator will treat it as a GameGear game. If it's got a .sms, it will be treated as a Sega Master System game. It's not the header. It's not this footer that's actually checked by the emulators. These bytes could define it, but they actually ignore it. Now, as well, as I said before, we're defining a symbol called build SGG as 1, and this is used by the Hello World code. You saw it various places. I do also define an SMS one here, but I don't use it in today's example. That's optional. Beyond that, we are checking labels to make sure that no labels look like commands. If you accidentally don't put a tab before your return, the assembler will treat it as a label, but that will almost certainly be wrong. So that will warn us if we make that mistake. The source file is being specified here. We're outputting a binary file. Here's the binary file we're outputting, and we're backing up the listing to a text file. This is just for debugging purposes. You don't really need this. And then we're starting the emulator here, Fusion, and we're passing it the cartridge, either the Master System cartridge in this case, or the GameGear cartridge in this case. But you'll notice there's an extra command here, this binary tools command. This is only on the Master System, and the reason for this is the GameGear never checks the checksum. None of the GameGears check it. We could put it in there, I've just not bothered really. But how do we calculate the checksum? What is a checksum? Maybe you've not heard of it before. Well, a checksum is what it sounds like. It's a sum of all of the bytes within a range of a file, and it's a crude way of checking if anything's corrupted. If a single byte's corrupted, the checksum won't match. And the way it works on the Master System and the GameGear, although the GameGear never really checks it, is they sum all of the bytes from 0 to 7FF0, or lower if the cartridge is smaller. If the cartridge is larger, it still only checks up to 7FF0 though. So effectively we're summing every byte from this point all the way to this point. So this is not counting the footer, of course, but this is what it's doing. And so I've got this program I wrote called binary tools, and I'm telling it create a checksum of the file cart.msms, count from byte 0 to byte 7FF0, and store the result in cart.sms, the same file as we actually checksummed here, which that does work okay. And then we want to store it to address 7FFA, and the checksum is a 16-bit checksum. Now 7FFA is effectively these 2 bytes here. And so what we're doing is, once we've created the binary file, binary tools here is calculating the checksum and then patching the correct checksum into cart.sms, and this will work just fine. So now that I've unremmed this line, if I run this again, we've got no checksum error that time. So that is how we can create a valid cartridge that will run just fine on our emulator, even if it's got that later firmware. So this is a very simple example of just doing a hello world, or at least as simple as you can make it with a system like this with no firmware. But I do have a more advanced example here. This uses a piece of code called the monitor, which I created in the multi-platform series. This is effectively a software register monitor and memory dumper, and we're going to use this to show some parts of the system. So what we can do is we can call the monitor, and we can also dump an area of memory from 0, in this case quadruple 0, and we're going to show 32 bytes. So let's just run this and see what happens. So you can see we've got our old hello world message here. We've then got a dump of the main registers, stack pointer AF, BC, DE, HL, and the program counter here. And then we've got a dump of the memory here, and you can see 18, 7E, and all these C9s. And if you look at the top of our code, we've got a JR, which is 18. This is the program start, the offset to there, which I guess is 7E. I'm going to trust that's correct. And all of these C9s are our return commands, and you can see them just here. So this is designed for us if we're just starting out and playing with things, trying to test maybe a joystick reading routine or make some sound work. Hopefully this will help you out with debugging things if you're using an emulator like this that I don't think has any debugging functions at all. Anyway, I just wanted to show you that as an extension to the basic hello world function, just to show you that really once you can get a character to the screen, you can get a number to the screen, you can get a hexadecimal digit to the screen, and if you can get a hexadecimal digit to the screen, well, you can start reading in from memory or ports and showing that and really working out how things are going on and making something a lot more impressive. So there we go. Okay, so that's really all I wanted to cover today. I know this is a bit complicated, but as I say, with a system like this, you do have to sort of do a bit more legwork because you've got no kind of firmware ROM to do the work for you. If you're not familiar with Z80 at all, I always suggest the Amstrad CPC Win8. It's really easy one to get started and do just, get things running with just a few lines of code without having to worry about compilers and things. I've got a whole tutorial series on that, so if you're interested in that, please check it out. Anyway, thanks for watching today, and goodbye. Now, if you have questions, comments, or suggestions, please feel free to sign up to my web forums. Every tutorial episode has its own section on the forum. If you just click on these buttons here, you'll see it goes to a matching page of my forum. The forum's just at chibiakimas.com/forum. It's free to sign up, of course. You can show off your project you're working on. I totally encourage you to show us what you're working on. And if you've got any questions, any suggestions, please let me know them. It's purely an assembly forum. So if you're working on assembly programs and you want to show them off, please sign up and show us what you're working on. Thanks a lot.